My name is Lars von Buchholz, and my project deals with identifying cell nuclei by image segmentation. This project is based on this year's Data Science Bowl competition on Kaggle, and as I said, deals with the segmentation of cell nuclei in biological microscopy images. For the purpose of this project, all nuclei of a single image were collapsed into a common foreground mask, and we treat the problem as a pure foreground-background segmentation problem. To this purpose, we will use the so-called unit architecture and implement it in Keras to determine which part of the image contains nuclei. And this is the original paper dealing with units. So this is how our data looks like. The data was downloaded from Kaggle and consists of 670 RGB images from microscopy of biological tissue stained with various nuclear stains. And so here in the first column and in the third, you have the original images. And in the next column, you have the masks where the nuclei are located. That's what we are trying to predict. You can already see that there's great variation in the data. There is grayscale and color images. There's images coming from fluorescence microscopy with the dark background here, and bright field images. There's different magnifications, and there's tissue and isolated cells. And classical computer vision techniques would basically require different algorithms for all these different conditions to predict the nuclei. But we are using a ConvNet-based network to predict the masks. First, we pre-process the data, bring everything into the same format, and split it into 536 training and 134 test samples. So this here is the unit architecture. This architecture shares some features with autoencoders. The first half is basically a regular ConvNet with decreasing image dimensions and increasing filter dimension. The second half reverses this architecture to arrive back at an image with the original dimensions. However, this is not the original image itself, but the target segmentation mask that we're trying to predict. Additionally, there are symmetric shortcuts between layers in the first half of the network that feed high-resolution information back into the second half. So I ran this implementation on an iMac desktop with an AMD Radeon card, which surprisingly is supported by Keras. We're using Keras 2.1, TensorFlow 1.5, in Python 3.6, and I'm running most of that in Jupyter Lab, Jupyter Notebooks in Jupyter Lab. Auxiliary packages include pandas, matplotlib, scikit-learn, and scikit-image. So a brief overview of the implementation. First, of course, we downloaded the data, converted it. It comes as individual images, converted these images into a four-dimensional array. And we combined all the nucleus masks that come with a single image into a single combined mask and convert these masks into a four-dimensional array as well. Then we build and train a unit model, display the loss history, with this model predict the training and test set, and calculate and display the cross-entropy loss, and another metric that I'm going to talk about later. We also train a unit model with data augmentation because our data set is pretty small, and we visualize the prediction versus the ground truth for the training and test set images. So let me quickly switch over to the Jupyter Notebook here. So the first thing we do is we load the packages that we need, Keras, NumPy, pandas, scimage, scikit-learn. Okay, and so I'm running this here on a laptop, not the computer where I really trained all these networks, so I don't have good performance here, but I've saved pretty much everything away. I can just load up the data. So here we are importing the individual images and converting them into 4D arrays. We're also collapsing the individual masks into single mask images for each image. Then we do a train test split. And I've saved that data, and I'm simply loading that up again. Takes a while. And then we can just have a look at a random selection of data. Here it is. You can see how heterogeneous the data is, different types of stains, different intensities, and so on. So then I'm defining a function here to build a unit model. I'm feeding it a basic parameters of the architecture, so the number of filters in each block of the descending arm of the unit and the corresponding dropout rates. And then the function essentially builds this network. Here, this for loop builds these blocks. Then we have a middle layer, which is the same as in the first half of the layer, just missing the max pooling. And then we have the second half of the unit, which contains this conv2d transpose function, which is upsampling the images, so making it larger again in the image dimensions. So I'm just defining this function, build a model. And here you can see we're starting out with 256 by 256. They are RGB images, so 3 channels. Then we have 16 filters in the first block. And then in the next block here, we're going down with the image dimension and up with the feature dimension. And that goes down all the way to 16 by 16 by 256. And then we're going back up all the way. And in the end, we have a sigmoid activation function that gives us probabilities for foreground. That's in this last convolutional layer. We end up with a 256 by 256 by a binary mask. So I cannot train this on here because even starting up the model before the first epoch starts would take too long. But I've saved the history of the training. I'm loading this up here and displaying the loss over time. And you can see that the training loss in blue declines nicely over time. It so I employed an early stopper to conserve computing time and also make sure that I'm not overfitting to the train set. So as soon as the validation set does not improve anymore, the validation loss is here in orange, I'm stopping the model if it doesn't improve for 5 epochs. There's a funny bump in here, but obviously it caught up again and then continues to train nicely. Then I'm predicting the train and the test set. Again, that takes forever, so instead I'm only loading this data up. And I've also converted these probabilities into Boolean masks so that those would be my final output masks. Here I'm loading those up too. And then I'm defining some functions to evaluate the quality of the model. One is just calculating the cross entropy, binary cross entropy. And the other is an additional metric that's frequently used for segmentation tasks. And that is the mean IOU, or intersection over union. So it essentially counts, it overlaps the prediction with the ground truth, and the overlap of the two would be the intersection, and we divide the size of that area with the size of the union of both areas, and that metric tells us how how much relative overlap we have between ground truth and our prediction. So we define these functions and then calculate on our predictions. Should be there in a second. Yeah, we have very small training loss, and the intersection over union value is really good. So that's 81% here. To compare that with classical image processing methods and computer vision, they only achieve in the range of 60 to 65% on biological image tasks like this. The test loss is only slightly higher than the training loss, indicating that overfitting is not really a problem in this model. So since the dataset was so small, we also trained a model with image augmentation. Specifically, we used horizontal and vertical flipping because that was what was suggested on the Kaggle discussion board. So we define function for image augmentation, and I can't train the model, so I just load the history of it, plot the loss. You see it trains nicely, and load the predictions and see how they perform on our data set. And well, this is twice here. So we can see here that the augmentation model does not perform any better than the original unoptimized model. The loss is slightly higher and the intersection over union is slightly lower. So data augmentation didn't improve our model. Next, we're going to visualize our predictions. We are displaying composite RGB images with the prediction in the red channel and the ground truth in the green channel. So this results in correctly predicted nuclei pixels being displayed in yellow, whereas false positives are in red and false negatives in green. So this is a function to do that. And when we just randomly select some training samples, we can see a lot of yellow, meaning that the model performs really well. The same if we look in the test set. Yeah, we see a lot of yellow. And it looks a little bit as if the biggest problems are in these bright field images, and that might be because they are underrepresented in the data set. So in summary, let's go back to the PowerPoint presentation. In summary, it was quite surprising how well this first simple unit model performed without any type of optimization. The performance is considerably better than with classical computer vision techniques. So an IOU of 81 is very good. The model was not really optimized at all. I had taken the layer dimensions dropout rates from a suggestion on Kaggle, but that had not been optimized either. It was a little disappointing that data augmentation did not improve the model. And given that the biggest problems in the prediction stem from the bright field color images, it might be a good idea to apply data augmentation selectively to this subset of images to achieve a more balanced model. What I plan to do in the future is, so this was a basic image segmentation problem, and I want to try some instance segmentation on that data. And that's more in line with how the original data science bowl problem was formulated. And the technique that I want to use is so-called mask RCNN, a technique introduced last year by Facebook, and I'll try to implement that. Thank you very much for your attention.